Okay, in this video, I wanted to review a couple of op-amp circuits that show up in your textbook. Okay, so the first one is called an op-amp summer. Okay, so you might need to use something like this to add signals together in a control system, and so it's important to take a look at this. One thing I wanted to point out though first is that this is a shorthand type of notation for the circuit. You notice it's just this little minus terminal connected, and it doesn't show what happens to the plus terminal on the op amp. There's always two terminals. Okay, so let's put in the plus terminal, and this would be connected back to ground. Okay, and in fact everything is with respect to ground, so there'd be like a ground plane coming through here. This is connected, and V out would be with respect to ground, and V2 would be with respect to ground, and V1 would be plus minus with respect to this ground wire. Okay, so maybe that'll help you see that a little bit clearer. All right, so the analysis on this is very much like what we did before with the inverting op-amp example that I derived in the previous video. We assume the virtual short condition that V minus is equal to V plus. Okay, and so since V plus is at 0 volts, we know this point in the circuit is at 0 volts. Okay, so we can do sum of currents like we did before. Here's an I2. I2 would be V2 minus 0, because the other side of this voltage is 0, divided by R2. And I1 would be V1 minus 0 divided by R1. And then I out, referenced here, I out would be V out. And this is again 0 volts minus 0 divided by RF. Okay, so you can put all these equations together. I'm going to move them and write down the final answer. Those are the equations. You simply solve those for V out, and you get that V out is equal to minus R1 over RF V1 minus R2 over RF. I got that backwards, sorry. Hang on. Minus RF over R1 V1 minus RF over R2 V2. So there's the summer circuit. You can see it adds these two voltages together. It does have this minus sign on it. You know, you could, one thing that's nice about op amps is you can cascade those together. So you could do a non-inverting op amp that followed that would, an inverting op amp that would cancel the sign and get those to be a positive sum. Okay, so that's one example. The other example I wanted to show you, again, you put the plus in, you put the ground wire. All right, this looks a lot like an example we had already done where this was RF. Okay, so this is playing the role of RF. All right, so I'm going to erase that because it's a capacitor. And if you took the Laplace transform of the circuit, this would be 1 over CS. Okay, so we can immediately write down the output. V out is minus, remember the role before was RF, okay? So what plays the role of RF? 1 over CS. Okay, so 1 over CS divided by Rn times Vn. Okay, these actually should be, yeah, I kind of screwed that up. These should be Laplace variables now. If I take the Laplace transform, this would be a capital V out. This would be a capital Vn. Okay, so let me fix that. Okay, so V out is minus 1 over CS divided by Rn Vn. Okay, and so this, simplifying this, it's minus 1 over R N C S Vn. The point here is that there's a 1 over s. And so when we think of Laplace transforms, if we see a 1 over s term, we should think integration. Okay? And so this is called an integrator. This will integrate a signal. All right, and sometimes that's needed for the controller. We'll talk about PID control a little bit later in the course, but that's how you would implement an integration in a controller. All right, so here's that's the review of a couple of op-amp circuits.